Okay, so welcome back to the derivation of the Rayleigh inflection point theorem. What we have done so far, or just to recap what we were talking about, the basic idea was we wanted to prove the Rayleigh inflection point theorem, which says that as soon as we have an inflection point in the base flow, then this is a necessary condition for a linear inviscid instability. And this we would like to prove. What we have now already done is we wrote down the equation and we said, or we did the main point here, namely we did an integration in the vertical direction and we multiplied everything with V hat star, the complex conjugate of the disturbance, which will then allow us to get rid of all the complex parts in our derivation. Or yeah. So right now we're at the stage that we did this integral and multiplied with V hat star. So the next step now would be just to rewrite that in a slightly more accessible way. So we have this integral from -1 to 1. If I multiply or divide everything by UB minus C, which I can do except in the critical layer, but in all other points I can do that. And I'm working a little bit with these derivatives. I will see that the first term will just become d squared times V hat star minus alpha squared V hat star. This is in dy minus the integral from -1 to 1 of UB double prime divided by UB minus C times V hat star dy. And this should be 0. So this is just the same integral rewritten. Now, what we can see here is that that in principle, this term and this term, they're kind of easy to treat. In this term, I have the second derivative, so d squared of this V hat star. What I perhaps would like to do here is to evenly distribute this derivative d squared among V hat and V hat star. And of course, the way how to do that is to do an integration by parts. So the usual trick, if you have a second derivative and you have two terms that you would like to deal with. Well, if we do this integration by parts, we get the integral from -1 to 1 of V hat star times, well, d squared times V hat dy. And this would then be with the integration by parts, the boundary term, which is V hat star d squared V hat, evaluated between -1 and 1. And then we get the other integral term, which is the integral from -1 to 1 of d times V hat star times d V hat dy. So what the integration by parts really does is to distribute the second derivative onto both terms here. That's exactly what we would like to have. Well, and the boundary terms, that's the nice thing, the boundary terms will actually fall out because we have the continuity equation, so that means that or actually we don't even need the continuity equation, we just know that the velocity V hat star at the boundary is actually 0, so therefore this will just fall out. Okay, so what we get in the end, if we just essentially replace this term with this one, we get the integral from -1 to 1 of dV hat squared plus alpha squared V hat squared dy. That's in the integral minus what we had as the second term above, UB double prime divided by UB minus C times V hat squared dy. And this should still be 0. Actually, I think this should be a plus here. So now, if you look at this, the interesting thing is that these two terms, we can actually say something about whether they're real or complex. The first term, that is actually a real term because, well, it's just squares of something, and alpha is actually alpha is a real number. So that means that the first term is actually something that is real. The second term, on the other hand, the second term here may actually be a complex term. So this we don't know. The first term is real. The second term may be complex, and that comes from the fact that the C here contains, of course, alpha, which is the real wave number, but it also contains omega, which, as we know, may be, have an imaginary part growing or decaying. So the C here makes the second term potentially to be complex. So that means if we now want to simplify everything, realizing that everything needs to be zero, we need to, or we know that the complex or the imaginary part of the second term actually needs to be zero. So how we can proceed here is that we take the imaginary part of the whole equation, which of course just means the imaginary part of the second term, which is this integral of ub double prime divided by ub minus c, so minus 1 to 1 of v hat squared dy. So this imaginary part needs to be zero. Okay. Well, what can we do here? Not so much, because we have the problem that this, our complex value, the c, is in the denominator. We actually would like to have that in the numerator. So we do also here the usual trick. We multiply by ub plus c divided by ub plus c. And of course, if we do that, it will not change anything, because this is just a 1, but it would remove the complex or the imaginary contribution from the denominator. So if we do this multiplication, what we get is then the integral from minus 1 to 1 ub double prime ci times v hat squared divided by ub minus c squared. dy is 0. So this is now the imaginary part of our equation. Now comes the argument of Rayleigh. So we see that this needs to be 0. If we now think of an unstable case, in an unstable case, Ci is actually larger than 0. That's the definition of an unstable case. The denominator is also larger than 0, as is this guy here. So we have essentially all the green terms are larger than 0, and the integral of those needs to be 0. Well, what does that mean now for ub double prime? Well, it means that ub double prime somewhere needs to change sign, because otherwise you could not have an integral over a domain to be 0 of only positive numbers. So that's the argument of Rayleigh. So for this integral, to be 0, UB double prime needs to be 0 at some point in the domain. Otherwise, you couldn't get that to work. It would not, the integral would not be 0. But of course, it's by no means a necessary condition. It's just, it needs to be 0 somewhere in order to be able to potentially have an instability. So this will be only a necessary condition for instability. And of course, instability means Ci being larger than 0. And of course, with this, we have proven our statement, namely that that this Rayleigh inflection point profile theorem holds true. Any unstable profile needs to have an inflection point, and then it could potentially be invisibly unstable. Yeah, what does this mean now? Well, let's have a look at a few potential profiles which we could discuss. Let's look at 4 different cases. Profiles. So, well, let's look at the jet flow first. So this is kind of a nozzle, fluid comes out from a nozzle, and then the profile would maybe look something like this. This was maybe not so nice. So something like this. This is the first profile. If this is I don't know, X, and this would be Y. So this would be the velocity profile. This is for a jet. Then we can look at a boundary layer, which we have done many times before. So we have a boundary layer profile that maybe looks like this. Then we can look at channel flow. Something like this. And then we can look at the kind of a separating boundary layer. So if you think back of a Faulkner scan boundary layer, but exactly at the point of separation or close to separation, where we kind of had a profile that looked like this. Now, of course, there's a kind of one interesting point here. These profiles that I drew here obviously were derived with a viscous based on viscous equations for the base flow, because otherwise you would not have no slip boundary conditions, because no slip boundary conditions obviously are a viscous effect. But that's kind of that's the idea here. We have a profile that may come from viscous effects, but now the question is, how does the instability on top of these viscous profiles look like? Does this allow for an inviscid instability? So now I have these 4 cases, and I would like to ask you the following: which of these 3 or which of these 4 profiles are actually or may be unstable when it comes to the wording of Rayleigh? Which of these profiles allow for an instability? What do you think? I have started a poll for you, which you can look at. And yeah, my question is, what do you think? Okay, very good, very good. I see the answers coming in, and Excellent. Well, I guess most of you actually have it right. So many of you say that the chat is unstable. Well, you know, what do we need to do? Well, we need to go in and look for inflection points of the profile. So profiles where the derivative, the first derivative, changes sign, or you can also view it like that, where the second derivative or the curvature of the profile is 0. If you now start with the chat flow, well, we actually have in this point here, we have, and of course in this one as well, we have an inflection point. So that means a chat profile. So if you have a higher velocity in the center than outside, this is something which actually may be unstable, invisibly unstable. And of course, invisibly unstable is a kind of an interesting aspect, or an interesting instability, because it means it's really based on the inviscid equations. You cannot stabilize it with just putting more viscosity or lower the Reynolds number. So that's the chat profile, which is invisibly unstable. Now the boundary layer, actually there is no change of there's no position where the curvature is 0, except actually here right at the wall. This is maybe something that is not so obvious, but if you look at the Blasius profile and you plot the second derivative of the Blasius profile, which would correspond to F3 prime, which is actually 0 at the wall. So there would be an inflection point right at the wall, but of course that's not really the same as you would have it somewhere in the domain. In the channel flow, you have no inflection point. There's no position where the derivative changes sign, or where you have 0 curvature. In the separating boundary layer, as also many of you said, actually you have an inflection point further away from the wall, which is very different from what you have in the boundary layer, because in a normal boundary layer, because this is further away from the wall, and it just shows you how unstable or how sensitive a separating boundary layer may be, because it is actually unstable from the Rayleigh inflection point profile. Okay, so that means we have now, using the Rayleigh theorem, we have now a way of determining what profiles may actually be unstable from an inviscid point of view. And of course, that's an important realization, because that gives us very quickly, just by looking at the profile, an indication of whether something may go wrong, or may become unstable. Now, there is actually a very interesting extension to the Rayleigh theorem, which is a second theorem, which was due to a guy called Fjørtoft. That's the Fjørtoft theorem, which actually goes back to Ragnar Fjørtoft, and he lived from 1913 until 1998. And I guess now you start to realize, now we're really getting close to well, times that we even start to remember. The theorem itself came from 1950, so that's when he published this theorem. And I will not. I'm not going to prove it here in class. I will just show you the result. The proof is not very difficult, and you can find it in textbooks if you're really interested. But we probably focus more on the application of it rather than the actual proof. But what it says is the following: for a monotonic velocity profile, a necessary but still not sufficient condition for instability is that the inflection point corresponds to a vorticity maximum. As I said, this is an easy proof, and I refer you to textbooks if you want to look at it. Now, so it's still only a necessary condition, so it didn't change anything in that point of view, but it essentially decides which of these inflection points may be unstable and which inflection points may not be unstable. So from that point of view, it provides a stronger yet necessary condition for instability. So some of the inflection points that are deemed unstable from a rally may actually be not unstable. And of course, that's already an important point. So what it means is from rally, we know that we need to have d squared ub dy squared to be 0 somewhere. And we can calculate now the vorticity of the profile. That's what the Fjørtoft wants. So the vorticity as a function of y would be something like dub dy. And now what we need to check is whether this quantity, so whether this vorticity corresponds to a vorticity maximum or not. If it's a maximum, it's unstable. If it's not a maximum, it is actually not unstable. And we can kind of do the same game as before. I'm not doing it with a poll now. I just show it to you as a result. So if we just look at three different types of profiles, so we have as a function of y, we have uv, and I do that 3 times. So well, let's just take 3 different profiles. We have something that looks like a channel. We have something that kind of looks like this. And we have something that kind of looks like this. So these are 3 different profiles that are potentially possible velocity profiles that we could look at. Now, if we just look at rally, rally would say in inflection point, then it's unstable. The first one we have just said this is stable from rally. The second one has an inflection point here, so that is potentially unstable. And the third one has also an inflection point here, which is potentially unstable. Now, the question is, what does Fjørtoft say? Well, for this, we need to draw the vorticity. And then we need to check whether this is a maximum or not. So I do that again 3 times for our 3 profiles. The vorticity and y, the vorticity and y. So, well, for the first case, The vorticity is something like that. That's just the negative first derivative. And there is no vorticity maximum here, so that means this is stable. Also regarding Fjortoft. And of course, that means that the first profile is stable, and that's what we said just before, that there is no problem there. Now for the second profile, well, how does the vorticity look like here? Well, it actually looks something like this. It goes to 0, or somewhere, and but it actually doesn't need to go to 0, but it goes to a low value. So maybe I should draw it differently. So it's probably something like this. But of course, it shows you now that the point where we had the inflection point here, this point here, does not correspond to a vorticity maximum. And that means, according to Fjortoft, this profile is stable. So that means Rayleigh said it's potentially unstable, Fjortoft said it's stable. So that means that a profile that looks like this is stable. Now, the last profile, which is very similar to the one that we had in the chat flow that we talked about before, there the vorticity would probably, vorticity would look something like this. And of course, here, in the point where we have the inflection point, we are actually experiencing a maximum of the vorticity. And of course, that means that this is potentially unstable. And of course, that means that the third case, so if you have a profile that is kind of bent in that way, these are the profiles that are prone to an inviscid instability. And of course, we looked at one, we mentioned this before, that this corresponds to what we would have in a jet. So we can essentially conclude that typical examples for inviscid instabilities, are exactly, jet flows where we have this type of shape close to the sides of a jet. Wake flows, which is kind of the same, it's just inverted, but also mixing layers, where you have two fluids with two different speeds next to each other. These are typical examples which allow for inviscid linear instabilities, because they're unstable both when it comes to Rayleigh, but of course also when it comes to the Fjortoft criteria. So just to draw it again, these three examples, jets, wakes, and mixing layers. The jet flow we have just looked at. That's kind of like this, where the velocity profile, that's not nice. The velocity profile would look like this, where we have the inflection points here on the sides with a vorticity maximum in these points. The wake flows are like this, when you have kind of an obstacle, where you have to flow around an obstacle, and then the velocity profile would kind of look like this. So you have a decrease of the velocity in the center. So you would have kind of the gradients like this, and the inflection points which again correspond to vorticity maxima. Or the last example, mixing layers, is when you have a kind of a splitter plate, and you have a velocity u1 which is larger than u2, and down here you have a velocity which is u2 which is lower than u1. Then you would get afterwards a profile that kind of looks like this, where you have these gradients in the middle, And of course, this would again be kind of an inflection point here with a vorticity maximum. So it's these kind of three prototype cases that are potentially unstable when it comes to an inviscid instability. And in particular, the last case here with the splitter plate is essentially the one that we have mentioned a few times, because this would really correspond to the Kelvin-Helmholtz instability. So Kelvin-Helmholtz, and that is the one that that we also watched in the video in the beginning of the course. Remember this guy with this channel, which was then inclined, and then you get this this shear layer in between. So the Kelvin-Helmholtz instability in that sense is also called a shear layer instability. Okay, so I guess this is all very interesting. I just have one additional question, because we have said above here that actually channels and boundary layers, they are actually stable for infinite Reynolds numbers, which is a little bit kind of interesting, because you would expect that, because we know that channels and boundary layers, they are actually unstable for finite Reynolds numbers. And then suddenly they become stable again for high Reynolds numbers. And as we said before, that, I mean, typically you would expect the opposite to happen. You would expect that if the viscosity starts to increase, or the Reynolds number goes down, you would potentially think that the instability could be contained, could be dampened, or the growth rate could be lower. But it seems that for channels and boundary layers, exactly the opposite happens. And of course, that's something that's quite interesting, and we will talk about that after the break a little bit more. But before the break, I just would like to write down the comment. So, well, Poiseuille and the boundary layer, or actually I should maybe mention Blasius, profiles are stable for Reynolds going to infinity according to Rayleigh. Of course, here the question is, why is this actually happening? Or is there a way of understanding this? And this is what we will talk about next hour. So let me now stop the recording.